Many business interactions involve future payments. For example, a basic credit card transaction involves you agreeing to give the bank who issued the card the purchase cost of whatever it is you're buying at a future date. And in exchange, the bank gives the seller the money to cover your purchase today. Now, this puts your bank at a disadvantage, right? They could have used that money to do other things, expand their business, invest it somewhere, and so forth. So, to offset this disadvantage, you agreed to pay back something more than the amount you actually borrowed, right? And this extra amount is what we call interest. So, let's look at a specific example. Suppose you borrow $100 at 5% annual interest. So this means that at the end of the year, you'll owe both the original $100 and an additional 5% of that, or $5, for a total of 105. Now, these two numbers illustrate the two concepts that are going to drive a lot of our work for the next several lectures. So I've got some definitions here, right? The future value is the amount that an investment made today will be worth after a fixed period of time. And the present value is the reverse of that. It's how much you would have to invest today to end up with a given amount. So looking back at our basic interest example here, 105 is the future value of $100. And looking at it the other way, $100 would be the present value of the $105, since that's the amount we would have to invest to end up with that amount at the end of, in this case, the year, or however long the investment runs. So suppose you were to take that $105 that we earned in the previous example and leave it in the account for a second year. The interest for the second year would not be just $5. It would be 5% of the $105 the investment was worth at the beginning of that second year, or comes out to 5.25. So this situation where interest is earned at regular intervals and applies both to the initial investment and the interest earned in previous periods is what we call compound interest. Now, doing these repeated interest calculations over even a relatively modest time frame gets tedious pretty quickly. So fortunately, we have this formula here that we can use. And so let's look at the pieces of this. Think of that as the amount or the final amount. This is the future value. P, the finance term for this, is called the principal. That's the initial investment. It's how much we put in at the very beginning. R is the interest rate. T is the time. That's the length of the investment, usually in years. And N, well, this N and the N in the denominator down there, is the number of compoundings per year. In other words, it's the number of times per year we're going to enter interest. So, for example, quarterly would give us n equals 4, semi-annually would be n equals 2, and so forth. Okay, so let's look at some examples. Suppose we take our $100 investment from the previous example, and we'll stick with our 5% interest rate and a 1-year investment. And what I'd like to do is calculate the future value based on some different compounding intervals. Right, that's what I have here in this table. I'm doing this for a year, doing it semi-annually, that's twice a year. 4 times a year is quarterly, 12 times a year is monthly, and 365 is daily. Every day for a year, you would be getting interest added into the account in that scenario. So, if you'd like some practice using the formula, you can pause the video now, try putting those values, some of those values in, working them out, see what you get. I'm not going to bore you with some relatively simple arithmetic calculations, so I'm just going to fill in the table with the final results so we can discuss them. Okay, now these results are a little surprising. In the first scenario, you're only getting a single interest payment, right? That's one interest payment for the entire year. In the last one, you're getting 365 interest payments. You could have reasonably expected the future values to be blowing up, or in calculus terms, going off to infinity. But that's clearly not what's happening here. So to see what's happening, let's think about the extreme case, where the interest is compounded continuously. That is nonstop across the entire time of the investment. So to get that value, I'm going to take the limit of our formula here as n goes to infinity. And I'm going to call the result a sub c. Right? That's the limit n goes to infinity p 1 plus r over n to the nt power. Now, when we do that, the expression inside the parentheses becomes 1, but the exponent becomes infinity, which is one of the forms we saw back in the first semester that can be evaluated logarithmically using L'Hopital's rule. And so to do that, I'm going to take the logarithm of both sides. So the log of AC equals the limit n goes to infinity log p 1 plus r over n to the nt power. All right, now I'm going to apply some logarithm rules. Right, I'm going to split up that product, and I'm going to bring that exponent out. So this is going to become the limit n approaches infinity times the log of p plus nt times the log of 1 plus r over n. All right, now I can take the limit of the two parts of this sum individually. And that log p part, there's no n in there, right? With respect to n, it's a constant. So the limit as n goes to infinity of the log of p is just the log of p, plus the limit n goes to infinity of this second part, nt, don't forget the logarithm, nt log 1 plus r over n. All right, now as we let n go to infinity, this part here goes to infinity. The part inside the logarithm goes to 1. The logarithm of 1 is 0. So I've got infinity times 0. And we can turn this into one of L'Hopital's rules. One of the forms we use when we apply L'Hopital's rule. So this is the log of p, indeterminate form. Sorry, that was the word that wasn't coming. So this is the limit n approaches infinity log 1 plus r over n over 1 over nt. Okay, so now the numerator and the denominator, they are both going to 0, which is exactly the scenario we want to apply L'Hopital's rule. So I'm going to differentiate the top and the bottom. So we have log AC equals the log of P plus, when I differentiate the numerator, this becomes 1 over 1 plus R over N times R times the derivative of, sorry, it's not X, is it? We're differentiating with respect to N. dN 1 over N. I'm just going to leave it like that. You'll see why in a second. Right, now let's go ahead and do the bottom. We differentiate the bottom. This is 1 over t times the derivative of 1 over n. Now you see why I didn't want to bother messing with it. I've got it in the numerator and the denominator. I can cancel these out. And I left out the limit. Got to slip the. I get so focused on doing the derivative, I forget I still haven't done the limit yet. And so this is the log AC equals log P plus the limit as n goes to infinity. And now we're ready to do that limit. But I'm going to clean up the fraction first. This is the log of P plus the limit n goes to infinity RT over 1 plus R over n. Now we can do the limit. Right? The only n is down there in the denominator. The denominator is going to go to 1, which means this whole thing is just equal to the log of P plus RT. And let me write this in over here. This is the log of AC, because now I'm ready to get rid of that logarithm. Right? I'm going to raise e to both of these powers, and we get AC equals e to the log of P plus RT. Right? And let's clean this up a little. This is e to the log of p times e to the RT. E to the log p is just p. So this is p e to the RT, and that gives us our formula. Right? That is my formula for continuously compounded interest. So I've got our formula here on the left, which gives us A. Now remember, A, this is the future value of the investment P. Right? Now what I've done on the other side here is I just took that formula and solved it for P. Right? I divided both sides by e to the RT. Right? So this gives us a formula for P, which is the present value required to get a final investment A. Right? So we're going to kind of be doing this a lot as we go through the next several lectures. We're going to try to do something for the present value, and then we're going to turn around and see, well, okay, so can I do it for the future value? Now, in practice, you're never going to see a bank account or investment that gets this kind of interest. However, this is a useful result in financial analysis since it gives us an effective upper bound on the possible interest earned by an investment. And as we'll see in the next lectures, large corporations, they get payments on a sufficiently regular basis, companies like Amazon and Target, that in practice, their payments can be considered continuous, right? Which is what's going to let us bring in these two formulas to help us answer some questions. Okay, so in the next lecture, we're going to look at an application of this. There are actually other ways that we could do it, but it's a good application to illustrate how we can apply these formulas. And it's also going to demonstrate a way of thinking about these problems where we split them up into different time periods. That's going to be really useful in the following calculations.